We're finally done with the backpropagation introduction in Spiral. So what comes next? In a word, evolutionary algorithms. For the next stage, there are three substages that need to be cleared. First, we need to train the underlying neural model, which is the base, using a particular evolutionary algorithm. What algorithm we'll use for that will be up for discussion. After that, on top of the base, there will be a tabular model that we'll train using tabular counterfactual regret. This is something that we've covered in the previous videos. We've implemented a version of that in F#. And lastly, once all of that is done, we'll need to implement subgame solving to get that last bit of performance. Subgame solving is in fact just a tabular CFR, except training a tabular model on the complete game. We just train a model on a subset of the game. But that what I mean is, suppose there has been some checking, calling and raising, and that particular history creates a subgame. Because in order to actually solve the game at that point, we only need to solve that particular segmented section of the game. These last 2 points, we won't focus on them much for the following section. Instead, what we'll focus on is the evolutionary algorithm itself and its implementation. That was the thing that really tripped me off 3 years ago. 3 years ago, I bet, I won't say actually I bet too much in terms of money, but I pinned all my hopes on deep reinforcement learning. And it's not like I had any illusions about it. I knew that the algorithms are bad, that they had many flaws, especially regarding stability. But I thought that if I put in the effort, that I'd be able to make some innovations that would allow me to get around the disadvantages. And it was a complete failure. Back then, I could have tried using evolutionary algorithms, but it wouldn't have worked. And the reason for that is because the setup that I had back then would have been too inefficient. Back then, I only had the game on the CPU, and I wasn't aware, even though it was 2021, and it would have been possible to implement then what we will be implementing now. I simply didn't know that it was possible to implement everything on the GPU. My impression of the GPUs back then was pretty much unchanged from 2017 and 2018. And back then, the GPUs were basically toys. But now they're much more than that, and you can do some pretty serious programming. Back then, for example, the global grid synchronization using cooperative groups had just come out, and I didn't really think too much about that. Back then, I expected that some hot new hardware would arrive by 2022, and that was the whole purpose behind the creation of Spiral. I didn't have too high of an opinion of Nvidia. I mean, even right now, if you asked me how would I rate its software stack, I'd rate it 3 out of 5. And because of that, it gave me the wrong impression that a nimble startup could come in and easily outcompete it. But now it's 2024, and the AI startups are all useless trash. They're not worth paying attention to. If anything good is going to come out from AI, in terms of AI hardware, it will be from Nvidia. Maybe something will come from the hyperscalers like Meta, Google and Microsoft, but I doubt they'll be able to beat it decisively. At most, the increased competition for Nvidia and the AI bubble popping will result in sharply reduced hardware prices, which will allow us to buy Nvidia GPUs cheaper. So that's why I did a pivot. I have to admit, while I was doing the FPGA videos, I really was very desperate because, I was expecting AI hardware to come and it didn't come. So it feels like I was living in a bizarre world where nothing was happening the way I wanted it to. So, I heard that the FPGAs were really hard to program, so I decided to take a risk. Maybe I could do something on FPGAs with Spiral. But the difficulty in programming FPGAs doesn't have to do much with the programming language we are using. I mean, it does. I definitely think that programming FPGAs with Spiral is a lot better than using C++. But there's nothing I can do with Spiral to, for example, make its compilation times faster. Or, for example, take the latest Xilinx FPGAs. They have the FPGA fabric, and they have a completely different programming model for programming their AI cores. And they have a different programming model for programming their CPUs. And none of that is in any way integrated. They expected that to program the Xilinx FPGA, you'd need a whole team. At least that's the impression that I got from its documentation. So that also falls into the useless trash category. And lastly, the Xilinx FPGAs aren't even available. You can't buy them anywhere at all. Even the cheapest chip has, which is like $2,000, and that would be way worse than a high-end Nvidia GPU. It still has a lead time of 8 weeks. And for the higher-end cards, which cost like $20,000-$30,000, you'd have to wait half a year. So who's going to deal with that garbage? So the Nvidia GPUs are the only choice. You might think that maybe AMD GPUs would be a secondary choice. And while we're on that subject, let me show you a little thread. Letter to AMD, ongoing AMD hardware software firmware problems. This post is hilarious. I won't really quote it in full, but what it's complaining basically is that the GPU cannot be reset properly without taking out all the instances on a particular server. So, for example, if you have a single GPU on a server with many different GPUs, apparently these firmware issues require a complete server reset, which might affect other instances on the cloud. And basically, if you look at this thread right below, I think one of the it's basically the ability to turn it off and on again should not be a low priority additional feature. This is what AMD users are complaining about when it comes to their GPUs. And this thread, for example, is full of stories of people who used AMD GPUs and dropped them to switch to Nvidia. Like one guy would say that he spent so much time tweaking around the AMD GPUs that if his time was paid a minimum salary, he would have made enough to afford a much higher tier of Nvidia GPU. Here they are complaining about high idle power. And the GPUs apparently draw something like 100 watts when you have multiple monitors, even when idling. And that costs a lot in electricity. For example, 100 watts would be how much my 4060 low-end consumer GPU uses at full power. 110 actually, but it's close enough. And AMD software support has been poor for decades, even though they could have made a lot of money had they entered the AI race. For example, I think that AMD, even if it didn't believe in AI, because who knows, maybe it's a bubble, maybe it would have wouldn't have gone anywhere. But that's really no excuse for having poor software support and poor drivers, in my opinion. So the fact that AMD has such issues is proof enough that it's incompetent as a company. It really doesn't do much good to have good hardware when you have everything else around it. That's bad. Even if Nvidia was 2 or 3 times more expensive, it honestly doesn't matter much. One of the interesting things that I've found out in this thread, I think that DaVinci Resolve, which is the video editing software, the one that I'm using for all of these videos, actually doesn't support AMD cards because of all the issues that they have. If you have an AMD card and you ask the Blackmagic support for why it isn't getting used, they just send you over to Nvidia and tell you to buy that instead. And apparently the usual pattern with AMD is that their public representatives would find errors such as these. They make a lot of promises to fix everything, and they do nothing with that. And this is a pattern that has been going on for decades. So if possible, you want to avoid AMD at all costs. Who knows, maybe Intel will come up with something, but as I said, the track record of AI hardware companies has been abysmal, apart from Nvidia, which gets a passing grade. Back in 2018, 2019, I read that there were like 100 hardware startups working on AI chips. And now it's five years later, and apparently absolutely nothing has happened from all that effort. I cannot simply emphasize enough how disappointed I am by all of this. I certainly wasn't expecting that I'd be programming Nvidia GPUs in 2024, but here we are, and it's the best choice. So if you have an Nvidia GPU and you plan on buying more in the future, that's probably a good decision. We can wait 5 or 10 years to see if maybe TensorTorrent will get a handle on something, but it will probably go broke. GrabCore will certainly go broke. Grok has decided to even stop selling their hardware to customers. Instead, they'll just be a cloud service. I mean, take Grok for example. Just to run a single large language model, you'd have to buy like 500 Grok chips at total cost of 10 million, which is fucking ridiculous. And they can only do inference, while all the interesting uses of AI are in training. GrabCore was an early entrant, but it came out with these large servers which are like $10,000 and more and pop, and they only sold to data centers. So nobody programmed them, no ecosystem grew up around them. And now we can take TensorTorrent. These grayscale chips that came out recently were actually created in 2020. I argued with some guy on Hacker News who told me exactly that, but until very recently, these grayscale chips were basically unavailable. They weren't being sold anywhere. You'd have to maybe get in touch with the company to buy them in bulk or something like that. So in 2024, they're selling very outdated hardware on all the process nodes. One estimate that I read for the grayscale cards is that they are 2 times more expensive than the Nvidia 3060 low-end GPUs, but they are 3 times as slow. So that's basically the deal that TensorTorrent is giving us. And they expected that somebody like me would come in and start programming that. They're insane. From AI hardware companies, I was expecting a 10x boost over Nvidia, not a 10x step down. I was expecting them to be 10 times better for the same price, not 10 times worse. So I'm fucking pissed at the AI hardware companies. As far as I'm concerned, they're all fucking garbage, and I'm going to treat them, any such companies in the future, as such until they've proven themselves. And I expect that to not happen. And you shouldn't either. Don't be a fucking idiot like me and have more realistic expectations. Sorry, this rant wasn't really planned, but I'm glad that I got it out of my chest somewhere. Now let me catch my breath, and we're going to talk about this part here, training the underlying base model using an evolutionary algorithm. For the past few days, instead of programming, I've been doing research and thinking about which evolutionary algorithm we're going to be using. Because even though I've made my decision to use an evolutionary algorithm months ago, I wasn't actually sure what we were going to use until very recently, like in the past week, like in the past few days, I only come to a decision. And you should find that interesting, because the algorithm we're going to be using uses aspects from other algorithms, but it's not something that's been published. I'm going to explain my reasoning as why we are going to be using it. Let me catch my breath for a moment. Our main focus will be the Cross Entropy Method. In case you're wondering what that is, and you aren't familiar with it, have no worries. I'm going to explain it right now. Imagine you have a bunch of one-dimensional points on a line, like this for example. These circles are supposed to be points. Yeah, perfectly drawn points, as you can see. And if you have a bunch of points like this, what you could do is first calculate the average point, which would be something like here, and then around that you can calculate the variance using the usual formula. Let me write that out. You can see it here in spiral pseudocode. Imagine this X is an array. So if to calculate the average point, we'd first take the sum of it and then divide it by its length. Then to calculate the variance, we'd first center the points based on the average point, and then we'd square all of that and then take the average of it. And that's the usual variance formula. Then once we have the variance, what we could do, once we have this, we'd have something like this bell curve. And using that, if you think about it, we don't really need the original points anymore. What we could do is, for example, get rid of them And just using that bell curve, we could sample completely new points, and we'd get something like, maybe we'd get a, excuse me, maybe we'd get something like this. Maybe we'd get every once in a while something pretty rare, like here, but most of the points would be around the mean. Now, here is what the cross entropy method does. Suppose we generate a bunch of points like that. And in the cross entropy method, they won't be just points in one dimension, but in many more dimensions. We'd run the game on the, using these points, we'd run the simulator and get the reward at the end. And maybe it would turn out that, for example, these points here, they'd get very poor reward. Like they could be, for example, very poor poker agents. But these points here, especially the ones to the right here, these would be very good. So there are a bunch of things we can do at that point. For example, we could reweight these points so they have a very low weight, or we could just get rid of them completely, like that. And then we could calculate the average point using just this tree, and then calculate the variance of that. And when we have the average and the variance, we can make a new bell curve, something like that. Maybe it would be a bit more narrow in this case. Who knows? And now we could iteratively repeat this process. We don't need these points anymore. We'd generate a bunch of new ones. We'd get a bunch of points here, maybe one here, 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 here. Maybe we get a few here. And now we'd evaluate the method, the points again, using the simulator or a game or whatever. And it will turn out that these points are very weak. They are very poor poker players compared to the rest of them. Now, in order to get now the new average point and the variance, we just get rid of these, calculate the average point and the variance based on just these 3 points here, and then get the new sampling distribution, and so on. This is the way the cross entropy method works, and it was invented sometime in 2005. I don't exactly remember the algorithm, the paper in which it was introduced, but on game playing tasks, it was actually the top performer until later the covariance matrix adaptation method evolutionary strategy was invented, and it's still very good right now, because it's kind of like the CEM, which is the covariance, the CMA, covariance matrix adaptation method, except it only uses the diagonal of the covariance matrix. If you don't know what that means, it doesn't really matter too much. But the methods are basically related. And on something like Tetris, I'm going to dig up the reference just for that. So I'll pause for a bit here. I found this paper, Learning Tetris using the noisy cross entropy method. Let me quote the abstract. The cross entropy method is an efficient and general optimization algorithm However, its applicability in reinforcement learning seems to be limited because it often converges to suboptimal policies. We apply noise for preventing early convergence of the Cross Entropy Method using Tetris, a computer game for demonstration. The resulting policy outperforms previous reinforcement learning algorithms by almost 2 orders of magnitude. By previous reinforcement learning algorithms, I'm guessing they mean stuff like policy gradients. Now, I couldn't get the PDF, though I probably would be able to find it on Library Genesis, but I did find this paper. Take note, this paper is from 2006, and the Cross Entropy Method was released in 2005. This paper is from 2009. September 2009. Let me quote this abstract. In the previous, actually before I quote it, let me just note. The main innovation in this particular paper is not the cross entropy method, but the fact that they use noise. And in this paper it has some good graphs, and they elaborate the method. Let me quote the abstract. For playing the game of Tetris well, training a controller by the cross entropy method seems to be a viable way. We consider this method to tune an evaluation-based one-piece controller as suggested by Zita and Lorinch, and we introduce some improvements. In this context, we discussed the influence of the noise, and we perform experiments with several sets of features, as those introduced by Bersekas and Selixis. Okay, I won't try to pronounce all of these names. This approach leads to a controller that outperforms the previously known results. On the original game of Tetris, we showed that with probability 0.95, it achieves at least 910,000 plus or minus 5% lines per game on average, which I'm guessing is a lot. I'm not really familiar with Tetris that much. On a simplified version of Tetris considered by most research works, it achieves 35,000 plus or minus 20% per game on average. We used this approach when we took part with the program BCTS in 2008 Tetris domain reinforcement learning competition and won the competition. Now we won't read all of this, but I want to demonstrate. Okay, this is something. These are the features that we're using. They probably had a linear vector. I remember reading these papers years ago. They mentioned they had something like 22 features, and those features were like in a linear vector, real valued vector of floating point values. That is. And you have things like landing weight, eroded piece cells, row transition, column transition, holes, board wells. I basically have no idea what all of that is. And if you look here, okay, here is the actual algorithm. It generates the vectors, evaluates each vector, select the vectors with the highest evaluations, takes the mean, takes the variance. It's a very simple algorithm, and compared to the naive cross entropy method that I've drew out for you, the only real difference is that instead of just taking the new variance, the only real difference is that instead of just taking the new variance, they add some noise. Or let's name it epsilon. And now instead of having a distribution like this, you'd want to widen it a bit around the mean. And in the end, the way they reach convergence is that As the training proceeds, they lower this epsilon value progressively to 0. You have this is really a common trick when training neural networks using gradient-based methods. You have a scheduler, and you'd have a high learning rate at the start, and then gradually lower it as the training goes along. So this is the algorithm. It's very simple. It's not like some other algorithms where you need a PhD just to understand them. And here it is graphically. You start with a Gaussian distribution. This is a two-dimensional one. You have a bunch of points. You evaluate each vector with evaluate and select a proportion of the p best vectors. These vectors are represented in gray. Then you get the new mean and variance. Then you after that you have this ellipse which represents that mean and variance. After you added the noise, you increase the size of that ellipse. These mean and variance characterize a new Gaussian distribution that will generate vectors for the next iteration. It's very nice. I like this kind of algorithm from the start, but I think this is a really very general purpose. You can apply this method to pretty much anything. And as I mentioned, this was a very winning method back then. And if we're the main change that we're going to do. One of the main changes to this method that we're going to do is we're going to take a trick from genetic algorithms, and instead of completely getting rid of the previous points, we're going to keep them around, and instead only use this mean and the variance to generate a bunch of new points. In other words, we're going to leave in the previous winners. And I think that will lead to much stable training. This paper was published in 2009. Let me just pause a bit so I can see whether there is anything of more of interest in this paper. Oh, here is an interesting graph on page 7. What they're doing here is reproducing the original experiment, and all these lines represent the same algorithm but with different noise levels. This line at the very bottom is the algorithm run without any noise. It converges prematurely. With constant noise, it actually does a bit better than with linearly decreasing noise. But actually, I was going to say that it converges to a lower value, but I didn't see that this linearly decreasing noise actually is below the constant noise line. So the case is that the constant noise is the best, and decreasing it actually hurts performance, surprisingly enough. Let me see if there's anything interesting other than this. Here is an interesting graph. 10 executions without noise, and here are the 10 executions with constant noise. Without noise, you can see that the algorithm really depends heavily on where it gets initiated. Sometimes it gets very poor performance, and sometimes it gets much better. And this is my experience with with training policy gradient algorithms on something on a static games. Sometimes it would perform really well, and other times it would be horrible. But over here, with constant noise, sometimes it converges much more quickly, and sometimes it takes a while. But with constant noise, it always jumps out to the local minima, and goes to the maximum. And I'm really surprised. Are these like 80 iterations or 80,000 iterations? If I had to guess, I'd say these were 80,000. Oh, and this bottom graph, these are the executions with decreasing noise. It seems that it does better than with no noise, but the various lines end up not converging or converging prematurely. It actually isn't that much. The stuff in this paper isn't that much better than in the 2006 paper. But whatever, it's pretty good. Okay. The stuff in this paper uses expert features, but the interesting thing is that we'll actually be using the algorithm in our own work for actually designing such features. Okay, there's nothing more in this paper. Now let me think a bit what I want to say next. I think I want to highlight the deep neuroevolution paper. Just a second. I wanted to highlight this paper, Deep Neuroevolution. Genetic algorithms are a competitive alternative for training deep neural networks for reinforcement learning. This paper is from 2018, so it's like 6 years ago instead of 15. And I wish that something better than this came out, but it doesn't seem like the field has moved that much from very simple methods such as this being state of the art. And the title of this paper is a spoof on the OpenAI paper, which came out, who knows, maybe a couple of months before it. The OpenAI paper was this one. This is a paper by OpenAI, while the previous one was by Uber Labs. Evolution strategies as a scalable alternative to reinforcement learning. I think when this paper came out, this was one of the milestone paper in the field. What they're doing is using an evolutionary strategy algorithm to estimate the gradient, and the algorithm itself is really actually very simple. And I won't really go into it too much, but if you read the abstract, it says that the evolution strategy scales extremely well with the number of CPUs available. So they weren't even using GPUs for this experiment. Instead, this is the main advantage of of evolutionary algorithms, which is that they scale very well. And now that we have powerful enough GPUs, instead of using like 1,000 CPUs to perform an experiment such as this, we'll be able to just implement the entire environment on the GPU and get the benefit of that, instead of trying to get better efficiency through better algorithms, which was a strategy that didn't work very well for me. That's why we're going to be betting on this. But going back to this paper, in contrast to what was in this paper, OpenAI and DeepMind have a thing where they use very old algorithms, maybe put some spin on them, and they try them out on a very large number of machines and then report the result. And this is in the current field this is what's considered progress in the current field of machine learning, because the progress isn't much due to algorithmic innovations. I also think, you can definitely interpret this as a compliment to Nvidia, but this whole way of deep learning didn't just arise on its own. You could very well make the argument that Nvidia is what actually caused it by creating the appropriate hardware for it. If it wasn't for Nvidia and only Intel and AMD were players, maybe what we have currently in machine learning would have happened only much later. It's something to think about. Now, going back to this, in contrast to the somewhat novel algorithm which the OpenAI paper represented, this one uses a relatively old-school genetic algorithm, and those were invented in the in the 80s. I mean, that's what's at the top of my head. If I am wrong, please correct me in the comments. So, okay, let me study the abstract for a bit. Deep artificial neural networks are typically trained via gradient-based learning algorithms, namely backpropagation. Evolution strategies can rival backprop-based algorithms, such as Q-learning and policy gradients, on challenging deep reinforcement learning problems. However, evolutionary strategies can be considered a gradient-based algorithm because it performs a stochastic gradient descent via an operation similar to finite difference approximation of the gradient. Yeah, that's what was really surprising about evolutionary strategies from the OpenAI paper. They actually do something very similar to finite difference approximation. And that's the main reason why we don't want to use it, because in a multi-agent setting, it's going to be very unstable. I definitely want something similar to what genetic algorithms offer, simply for stability. Imagine it like this. In genetic algorithms, you have a population, and suppose you have a bunch of very poor players, but you also have an oracle that can play the game perfectly. If we tried actually optimizing that with something like an evolutionary strategy algorithm or the Cross Entropy Method, that advantage would get destroyed completely. Because you have 10 very poor players and one good player, and when you mix them together, you still get garbage. But if you're using a genetic algorithm, the entire population will start to converge towards those good parents. So I want to make use of that for multi-agent RL. Okay, let's continue from here. That raises the question of whether non-gradient-based evolutionary algorithms can work at deep neural network scales. Here we demonstrate they can. We evolve the weights of a DNN with a simple gradient-free population-based genetic algorithm, and and it performs well on hard deep RL problems, including Atari and humanoid locomotion. Now, before we continue, I want to show you a different paper. It was made by a somewhat cranky researcher, and I consider myself one of them. If you remember the rant from earlier, you can see I have a bit of crankiness in me. Let me pause here so I can locate it. It was about not using a genetic algorithm or an evolutionary strategy, but a simple random search. I think they used it on Mujoko, but I don't think they used it on Atari. Let me pause. Here is the paper. It's by Benjamin Recht. I really can't believe that this paper is from March 2018. God, the time flies. Let me quote from the abstract. A common belief in model-free reinforcement learning is that methods based on random search in the parameter space of policies exhibit significantly worse sample complexity than those that explore the space of actions. We dispel such beliefs by introducing a random search method for training static linear policies for continuous control problems, matching state-of-the-art sample efficiency of benchmark Mujoko locomotion tasks. Our method also finds a nearly optimal controller for a challenging instance of the linear quadratic regulator, a classical problem in control theory when the dynamics are not known. Computationally, our random search algorithm is at least 15 times more efficient than the fastest competing model-free methods on these benchmarks. We take advantage of this computational efficiency to evaluate the performance of our method over hundreds of random seeds and many different hyperparameter configurations for each benchmark task. Our simulations highlight a high variability in performance in these benchmark tasks, suggesting that commonly used estimations of sample efficiency do not adequately evaluate the performance of RL algorithms. At the time, I got the sense that this guy was really, fed up with all the garbage algorithms coming out, so he made this. And he basically, beat the benchmarks using random search, which was pretty ridiculous if you think about it. But it worked for him. And the method that we're going to be using isn't actually going to be that much more complex than random search. But, I'm not going to use random search because we do want some kind of mechanism to keep good solutions, inside the solution set compared to, evolution strategies from OpenAI or the bare Cross Entropy Method. And we also, need some kind of mechanism to drive the search. So we're going to take what exists in the Cross Entropy Method. But these papers really stuck in my mind because they really highlighted for me that it doesn't actually matter too much which algorithm we are using, as long as we have a fast enough program and the hardware to run it. Okay, let's continue from here. The deep GA, the deep genetic algorithm, successfully evolves networks with over 4 million free parameters. The largest neural networks ever evolved with a traditional evolutionary algorithm. These results expand our sense of the scale at which genetic algorithms can operate, suggest intriguingly that in some cases following the gradient is not the best choice for optimizing performance, and 3. Make immediately available the multitude of neuroevolution techniques that improve performance. We demonstrate the latter by showing that combining DNNs with novelty search, which encourages exploration on tasks with deceptive or sparse reward functions, can solve a high-dimensional problem on which reward maximizing algorithms fail. Additionally, the deep GA is faster than evolutionary strategy A3C, which is an actor-critic algorithm, and deep Q network. You can train Atari in 4 hours on one desktop or 1 hour distributed on 720 cores, and enables a state-of-the-art up to a 10,000-fold compact encoding technique. Oh yeah, this technique, I think they were using something like, instead of storing an entire network, they instead store a random seed used to generate a particular network, which is actually fairly interesting. It's a very nice compression method. You can use something like another number generator with a seed to generate all the weights for a neural network. And I can imagine you could apply this technique at the layer level and on the vector level, and you could use this very effectively to compress a neural network. We aren't actually going to be using that, but who knows, maybe we should. No, we won't. I won't back down on the method that I've decided upon. Because, it doesn't really matter whether the neural network can be compressed 10,000 times. For inference and for training, we still need to actually fully unpack it. So, this compression method is more like a curiosity than an actual advantage. You definitely don't want to generate each individual weight based off a random seed at that very moment, because it would be very slow. At least I think it would. And I consider this particular paper also one of the landmark reinforcement learning papers. It's only now in 2024 that not just these big labs, but I myself can use a desktop consumer GPU to actually make a good use of these algorithms. I'm just reading this lightly, and my voice is starting to give out. Let's get back to our own thing. Hopefully by now you understand what the Cross Entropy Method is, and you understand one of the changes that we'll bring in from genetic algorithms. There is also one other change. Let me pause so I can think about how to explain it. Okay, here's the first twist. Instead of getting rid of the old points and resampling them completely, we're going to use a mask and only resample the eliminated points. Because, we're going to have something like 64 different neural networks in the ensemble. And since we are doing things on the GPU, we cannot just, have them be separate objects, and for the ones that get eliminated, leave them to be garbage collected, and then allocate the new ones somewhere else. That would be inefficient. we're going to be using masks to mutate the dead losers. And on that note, I want to mention that it's actually pretty difficult to do even something like sort all of the points in the ensemble. Sorting is difficult on the GPU. So in order to actually rank them, we aren't going to be doing that specifically. Instead, what we will be doing is getting the mean and the variance. And then to get the top 10 or top 8 out of 64, we're going to eliminate all the points below a certain threshold of standard deviation. We're going to get something. We're going to sum up, all the rewards that have been gotten from the simulator for each of the agents in the ensemble. Find the average, then center it, then get the variance, and then take the square root of that to get the standard deviation, and then normalize by that. Then all the points will lie on this bell curve at around 0, and they'll have a standard deviation of 1. And then we'll mask out all the points below 0.7 or something like that to get the top 20%, or to eliminate the bottom 80%. That's what I mean. One thing that I realized because the previous papers did mention that without adding noise to the parameters, the cross entropy method converges prematurely to suboptimal solutions. And in those papers, the solution that I arrived at was to add a noise, and that was pretty effective. We could also do that as well, but I think one thing that would be better is to try pulling all the weights towards 0. This is something that we'll be able to do because we are keeping the old winners around, which the original cross entropy method wasn't doing. And why would that be beneficial, you might be wondering? Well, in a neural network, you actually want all the weights. You want the weights to be as close as possible to 0, and for as many of them to be 0. You want to induce sparsity. This is something that happens in the brain as well, and it makes very good use of that for efficiency. And it's a very good method of regularization as well, because sparse solutions are indicate a level of separability and understanding, while dense solutions are kind of like a jumbled soup. So what we're going to do is pull the weights towards 0. You know how we originally had this bell curve right here, and we also had the points in the middle of it. Then the bell curve started to get moved to the right. Well, when calculating this average point, what we could do... sorry, I didn't mean to erase all of that. Instead of making the average point right in the middle here, we could bring it closer to 0. One thing we could do, for example, is set it to 0 directly. Now, imagine the 0 is somewhere here. Let me mark it. Okay, excuse me, I need to straighten it out a bit, because yeah, now it's much better. And now I'll put in the 0 right here. Let me pause for a bit. I finally managed to mark it. It turns out these particular lines don't allow you to write stuff in between. You actually need to use the error in Excalibur. And let's consider what this would do in terms of the algorithm. Now the bell curve is basically right here in the middle. I mean, that's how it was previously. But if we were to assume that the average point is not in the middle of these points, but around 0, then the variance would get a lot wider to compensate. Basically, it needs to be something like this. And if we were to resample from it, as you can imagine, most of the new points would be at around 0. But they'd be dispersed much more widely. Like they'd be here, here, here. And in fact, searching at around 0 would give us great benefits for exploration. Even though the exploitation aspect would definitely suffer, because, you know, imagine with a regular cross entropy method, if we assume that the average point is 0 at every iteration, that's basically random search. All the winners would get kind of eliminated at every iteration in regular cross entropy, and the search would only go around 0. But because, you know, we are eliminating all the, because we are keeping around the winners, these are the points that would get eliminated, and our progress won't actually get worse by having such a wide variance. The only problem is that the points to the right of the curve would get sampled much more rarely. So that would be one of the issues, if you assume that, for example, the better solutions are more to the right. And let's think about what such an algorithm would mean in the context of something like a 4 million parameter neural network. You'd have such an ensemble, and all the winning points would basically just get for either flipped to the completely opposite side, or the algorithm would look at around 0. That's basically it. And that's not really good, because we don't actually want to optimize large neural networks like this. There would be some benefit to it at the beginning, but the overall noise would be too severe, I think. So a better approach would be to take the average and instead of having it come all the way to 0 at every iteration, it could be some kind of linear combination of 0 and the average. And the linear combination of 0 is just a factor of 0, so we don't need to write it out here explicitly. And the other factor would be something else. It could be 0.9, for example. Now, let's go back to how it was original. I'll lower the size of this. Uh, yeah, now it is. Let's assume this is how it was before. I won't undo it completely. But let's assume this is the collect bear curve at this average point without this the factor being multiplied by it, that is 0.9. And if we were to add, if we are going to lower the average point, by necessity, the mean would go towards the left, like something like so. But the variance would also get much wider, something like this. And this would inject the necessary noise to make the exploration proceed. Honestly, this is something that I just made up like a few days ago while I was thinking about it. Originally, I wanted to just bring the mean to 0, but realized it would be a bad idea. And then came to this compromise, which should be a lot better. And this is what we're going to use. As far as I know, this method hasn't been published anywhere. So we can call this, instead of the Cross Entropy Method, we could call this Ghostlike Cross Entropy Method. GCM. Ghostlike's Cross Entropy Method. Based on what the random search experiments are telling us, and what the genetic algorithm experiments also told us, the learning algorithms themselves don't actually matter too much. We just need to make sure we have a way of keeping around all the best solutions. And that's very important, especially for multi-agent settings, because we aren't at every optimization round, the environment will change. So that would actually completely break the gradient-based methods on its own. Let me show you a little thread that really highlights that. It was posted a few days ago on the reinforcement learning subreddit. It's this thread here. How difficult is it to train DQNs for toy multi-agent RL problems? And here the poor guy took a deep neural network, the ones that are going to become sentient and usher in the singularity, and which are supposedly already sentient, as demonstrated by ChatGPT. And he wanted to train them on something as simple as tic-tac-toe. I can only assume it had something like 9 tiles, 3x3 tic-tac-toe. And to his great surprise, these neural networks don't converge. And you have these two realities. On one hand, you have OpenAI and DeepMind, which solve Go, and then people come in and try to use these methods to beat tic-tac-toe, and they don't work. Anyway, enough with the rant. I like to ask if it's really that difficult to train DQNs for MARL. You can share any experiment with a set of parameters working well for tic-tac-toe. That would be very welcome for curiosity's sake. And now the knowledgeable people come in and they say, yes, it's very hard to solve even seemingly simple MARL environments with RL techniques. And DQN is not meant for that at all, especially if you're using a reply buffer. The problem does not come from hyperparameter tuning or lack of exploration. It comes from the high adversarial non-stationarity of multi-agent learning environments, which breaks the fundamental assumption of single agent RL. Your agents are not learning to play against random opponents. They are learning to play against themselves if you are using self-play, which is an adversarially moving target in terms of the underlying learning process. Trying to tackle MARL problems is a common mistake for beginners, as the theory behind it is extremely involved, and there is no way one can understand what goes wrong in a multi-agent setting without a strong understanding of single-agent setting. I think this last part is fucking bullshit, because the problem is that the algorithms are shit, not that the guy doesn't understand what the problem is. Not because the guy doesn't understand the single agent setting. And we basically know what we need to do in order to make the multi-agent setting work based on tabular CFR. If we take tabular methods on in adversarial multi-agent settings, what you would find is that the policies oscillate widely. Imagine you are training on something like rock, paper, scissors. The way the training procedure would go is that the agent would learn to, for example, play scissors 100% of the time. Then its opponent will learn to play rock 100% of the time. Then the other agent would learn to play paper 100% of the time. And then the other player would learn to play scissors. And that would go around in an infinite circle, as the agents kind of cycle through all the available strategies. And the way to actually converge to a viable strategy is to average those strategies out. That's why in tabular CFR you use two arrays at each node, one for the average strategy and one for the current strategy, which is used to optimize the agents. And the analogy for that is very clear in deep RL, the one that uses neural networks. Instead of using a single network and doing point optimizations, we definitely should be using ensembles. But except even with ensembles, if you're using something like a gradient-based method, you'd lose the benefit of having the best players around. So that would be pretty convoluted. And by that I mean, in deep reinforcement learning, instead of something like supervised learning, the gradient itself is pretty much noise. If you look at some of the deep RL papers by OpenAI, back while they were training the agents on Dota or StarCraft, they used a batch size of like 10 million to get around that. While in supervised learning, you'd use a batch size of 100 at most, 128, 64, something at around that level. So, yeah, the lesson from that is that the batch size is, the gradients in deep RL are pretty much noise. And when you're optimizing the stuff with these methods, of course, the agent would do very weird things, even in a game like tic-tac-toe. I think since this is tic-tac-toe, if we did enough random restarts from different hyperparameters, eventually he would hit upon a good agent purely by luck. But at that point, you aren't even doing deep RL. You're just doing a random search with different neural networks. This is fucking embarrassing for the entire field. You constantly have newbies going into this sub asking why their particular network doesn't work. I'm And the answer is that because the algorithms are trash. It's not that that they are incompetent. So admittedly, in contrast to something like supervised learning, when you're passing a static data set into a network, having to actually create the environment and everything else does require a vastly higher level of programming skill. That is, if you are doing everything from scratch like we are doing here. If you aren't, then you have some choices. And on that subject, here's the thread that I posted recently, I think. Now, where the hell is it? Okay, let me do. Oh, here is my thing. I mean, you can tell that it was by me, by this ghost on the right. But I'm not here to talk about this thread, but this JAX-based library here. It's actually a pretty interesting thing. TLDR, we can leverage recent advancements in JAX to train parallelized RL agents over 4,000 times faster entirely on GPUs. Unlike past RL implementations, ours is written end-to-end in JAX. This enables RL researchers to do things like efficiently run tons of seeds in parallel on one GPU, perform rapid hyperparameter tuning, discover new RL algorithms with meta-evolution. But that's not really what's amazing about this. It's more than just vectorizing the agents or hyperparameter search. They actually gone the next step, much like we are, and they have created vectorized environments on GPUs. And when you put everything on GPU, you have end-to-end vectorized RL training on GPUs. And I'm pretty sure that this wasn't around in 2021. This blog post was published in April 2023, and it's actually I'm generally very negative on the research coming out from the machine learning research community, because they're just producing noise instead of actual advancements. It's kind of you have thousands of people entering the field, making machine learning papers, other papers, you name it, and none of that is worth reading in the slightest. None of that are any fundamental advancements. But this actually is a fundamental advancement. So it's really my privilege to showcase it here. If what we're doing here in Spiral is too difficult for you, maybe you can check out this the JAX stuff here, PureJaxRL, this JAX library, the JAX reinforcement learning library. I really like the exclamation marks here. They're pretty much shouting at the top of their lungs that they have something good. And I think they do, even though I never tried it out personally. I mean, if I was starting out in 2024, I sure as hell wouldn't spend like 3 years creating a programming language to do this first. Instead, I probably try to vectorize the poker game using JAX. And with stuff like this, you can get really a lot more value out of a single GPU. Using GenJAX on an A100 with 2K environments in parallel takes 0.05 seconds. That's a 1000x speedup. Arguably, this GPU is a lot better than the one I have, but even with my own, it would still be like something like 100 speedup. Minotaur breakout, which takes 50 seconds, which is like 3000 not 3000. Sorry, I'm trying to translate minutes into seconds, but it says that it's seconds is 50 seconds here, so I don't have to do that. This is like 5 times 50, so that's 250 times faster than running it on the CPU. And in the past you'd make up for that by running it on 500 CPUs, but now you can train it on a single GPU, and instead of renting out more CPUs, you can rent out more GPUs, and this is much better from a price perspective. I really like this kind of research. This is one of, I won't say it papers, but since it's a blog post, but it's a landmark work, and it was in 2023. And what they're doing here with the metalearning is something I want to do in the future. I'm probably going to, when all this is done and I have this agent, assuming I decide that I have enough resources for it, I'm probably going to do a genetic programming system in Spiral. One advantage that we do have in Spiral is that we don't need to actually vectorize the environments. Instead, we are implementing them straightforwardly for a single thread in a continuation passing style. And that's actually a lot easier to program than having to keep every single step vectorized. At least that's what I expect. When I looked at the Jax code, you're pretty much building up an AST in Python, and having to build an AST in another language is a lot worse than having an actual language. I don't think that machine learning is going to be done, like this in Python forever. But the way things are going, Python could stick for a very, very long while. You had the languages like Julia, now you have some upcoming languages like Mojo, and you don't really have to expect that they take the crown from Python. Who knows? Maybe if I am very successful in my own reinforcement learning work, something will happen and Spiral will get taken up. But for now, that hasn't happened. In order to get a lot of money, you need fame. And to get fame, you need success. That really worked for DeepMind and OpenAI. It didn't really matter at all, that their work on Go and StarCraft and defense of the ancients didn't result in any tangible fundamental advancements. Instead, they were just giant engineering projects of parallelizing existing algorithms or on very many machines. But it got them a lot of press, and that in the end got them investor money. OpenAI made the greatest pivot from being an open source company, releasing everything in the open, to being completely closed and doing everything for the money. The stuff they are saying about AI safety is basically just like a competitive mode. You don't have to take it seriously. Yeah, these guys wrote a bunch of papers on this, and I don't think the papers themselves are that particularly good. Except maybe something like this one. I kind of like this one because I think it says that the gradient-free methods can actually be better than estimating the gradient than the actual gradient methods. I think it says something like that in here. Yeah, I mean, in this paper. I mean, I'm not going to like look for it right now. Oh no, let's. Yeah, this is what evolutionary algorithm should I use? I asked this thing here. Yeah, I didn't want to. Originally, I thought that maybe using the OpenAI evolutionary strategies. Actually, but it has a bunch of disadvantages, like being sensitive to reward scaling. It's kind of like it is. It doesn't take the gradient directly using backpropagation, but it still estimates it. I think I have a video in Is The SIngularity Near on my channel, which explains what's the problem with the gradient methods. You have the gradients can shrink to zero, it can explode, and to begin with, it's not really a proper credit assignment method. What we want is a method that would tell us directly how much to move a particular parameter, instead of telling us how sensitive a particular parameter is. There is a huge difference between the two. And there were attempts at such methods, but for various reasons, they don't really work. Yeah, if possible, I would have liked to have used the covariance matrix adaptation. You know, at first the cross entropy method was the best method for reinforcement learning. Then the CMA came out, and it was the best. But it has polynomial scaling, so it's basically completely out of the question for training deep neural nets. Unless they had less than 1,000 parameters. Okay, here is basically a blog post, and it's my theory past. Okay, is there anything interesting? I mean, okay, here I'm basically getting into an argument with somebody who's, very, very bullish on today's AI. You have people who know basically nothing about the algorithms and only see results and conclude that the AI is going to become sentient in in this decade. But I don't think that's going to happen. Even though I really would have liked if that was the case. I mean, stable diffusion. I thought these AI generators actually predicted that they would appear, but I don't think they would be accompanied by such a huge lack of insight. I thought, if we had something of this level, that it would tell us quite a lot about the nature of intelligence, and these algorithms don't tell us much of anything except two things: that optimization is pretty magical, and that matrix multiplication is magical. That's basically it. All those hacks on top of that are just noise. Yeah, and ChatGPT is a suped-up character recurrent neural network. We had architectures like this back in 2015. You could train it on something like works of Shakespeare, and it would generate similar texts. And that was pretty fun for a while. I even trained such a network myself back then. I created a machine learning library in F# and implemented all of it from scratch. So I know that even if you go from recurrent neural networks to transformers, you don't have algorithms that are powerful enough to really get us to human level AI. And I want to highlight, it's not because there's something magical about the brain, and it's not because these algorithms are using non-linearities and linear algebra to get their results. Pure and simple, the algorithms themselves are simply too weak. That's what I want to say. With some different algorithms, like the ones that we'll have in the future, maybe in 10 years, 20, it's very likely that we're able to get human level AIs, even potentially on today's hardware. Okay, this was basically an ad hominem, so I don't downvoted it. And this is in fact what I do expect. The backpropagation is pretty simple, and I do expect that we'd have, specialized learning algorithms in the future for that can only optimize a particular class of models. Backpropagation is a very general method for optimizing mathematical expressions, and that's not necessarily something that we require for intelligence. What we require for intelligence is something different. Maybe it will be the case that backpropagation could be used in a limited fashion inside future neural networks to optimize for prediction in a self-supervised manner. Predict the next image or sound or text token. And, as been shown by ChatGPT, that works very well. But that would just be an internal aspect of the agent. What's really difficult is moving beyond that. And, even with backpropagation, the backpropagation doesn't have an answer for how to do, very long-term learning that lasts over days and weeks and years. Backpropagation has especially transformers, which scale polynomially in their context size. Backpropagation can maybe do 1,000 steps, 2,000, 4,000, depending on how much hardware you want to throw at it. But beyond a certain point, it cannot be used to do learning. And the biological brains obviously can do that, and they are very stable. They don't have issues with that gradient-based methods have. Okay, I have no idea what PGPA. Actually, I did do a search for that. I know what PGPA is. Policy gradients with policy parameter-based exploration. Yeah, I think this was like a paper by Schmidhuber. And policy gradients are trash. And Ray Tune Schedulers PB2. I have no idea what this is. Maybe it's some kind of AWS service. Oh, yeah, I'm really talking my lungs out here. Yeah, instead of adding the noise to the variance during the sampling, what we'll be doing instead is pulling the mean to a 0. I already explained that. This is how we're going to get good exploration. Maybe on top of that, we could also, add some epsilon. But the problem with epsilon is that then we'd have to make it a hyperparameter and to tune it manually, which would be annoying, and I don't want to do that. Okay, let's make this a big G. Whoops, what did I do? I closed the tab by accident. Yeah, you need to press escape in order to actually exit from this. Oof, I almost knocked over my mouse. I have this. I'm using this vertical one now, while previously I had this Logitech thumb ball, and it's kind of confusing me. Okay. Now, let me think. I'll pause for a bit so I can think whether there's anything else to say, or whether we'll just go into the programming. I've had a while to think about it, and nothing really comes to mind. So we'll end this very long introductory segment here and go into a time lapse. I hope you found this informative, and I hope that we're going to win this time around.